relationship between topological dynamics and C-star algebras.
All right, thank you. I'd like to thank the organizers for inviting me. This is my first time here. It seems like a good to do a seminar, so hopefully I'll be back again in the future. All right, so first let me go through some of the basics of what C-star algebras are about. So I'm going to give you a very quick and dirty definition here, and then try to proceed by just showing some examples. So a C-star algebra is defined to be a complete normed complex algebra A that has an adjoint operation star satisfying this certain norm condition. The norm of A star A equals the norm of A squared for all A and A. This is sort of what's considered the abstract formalization of this definition. The original definition, which was derived by von Neumann, Gelfand, Naimark, and several other people working in operator theory in the early 20th century, was a C-star algebra is a norm-closed subalgebra of the bounded operators on some Hilbert space. And so this gives a sort of concrete realization of the idea. And then they decided to abstract this and formalize it. But that's actually one type of example. I'm not specifically going to talk about that. But there's a lot going into this, because it's a complete normed algebra, so it's a Banach space that's also an algebra. It has this star operation, which I'll give some examples of, and it has this norm compatibility condition. Okay, so here we go. So first example, n by n matrices with the usual matrix operations. The star is the conjugate transpose, so that's the adjoint operation, and then the norm is the operator norm for matrices. And it turns out that, well, direct sums of these provide all the examples of finite dimensional C-star algebras. So finite dimensional C-star algebras are basically matrix algebras, so really complex numbers. Oh, there we go. Okay. Second type, take the continuous functions from a compact Hausdorff space X into the complex numbers. And with using the pointwise operations, the adjoint is the pointwise complex conjugation, and then you take the supremum. And these give all the commutative unitable C-star algebras. So all the C-star algebras that have an identity element and are commutative. Okay. So here now let's generalize the last example a little bit. Rather than have our functions be functions from a space X into the complex numbers, have them be functions from X into some other algebra. And again, use pointwise operations, and now you take the pointwise adjoint in the range algebra, and then again use the supremum norm. All right, so this is gives a generalization of the previous case. Now of course, if the A here is a non-commutative algebra, then this C of X comma A is also non-commutative. And so these give some examples, and we can actually obtain a lot of other examples from these sort of basic ones using universal constructions: direct sums, tensor products, direct limits, cross products. And there's lots of other ways of doing this as well. You can form the C-star algebra of a group, the C-star algebra of a graph. There's all kinds of other constructions of this type to get new ones from objects you already have. So just to see that the two types of examples we have can sort of give quite a bit, it's known that a lot of interesting C-star algebras are obtained in the following way. You look at continuous functions on spaces whose range are matrix algebras. You take direct sums of these, and you make a system of these, and then you take the direct limit. And there's actually a conjecture, which is still unresolved, as to whether all suitably nice C-star algebras, nice here, of course, being a bunch of technical conditions, if you take all of them of a certain type, do they all actually come in this way? Can you obtain them all as direct limits of essentially continuous functions over matrix algebras? Okay, so here's the basic idea behind what we call a classification problem. So there are lots of ways of obtaining C-star algebras, and a lot of them are given through abstract universal constructions and other things of this sort. So how can C-star algebras that be obtained through different constructions be distinguished from one another? Or how can we actually tell that two different constructions gave the same C-star algebra? So if you do a construction through a direct limit, or on the other hand you do one through something called a cross product, you're going to get two things that initially look quite different because of the way they're presented to you. But it could be that they're actually the same. And so this is what we call the classification problem, or sometimes referred to as, I'll go back. So what do we mean by classification? Well, we call a C-star algebra classifiable if there's something called an Elliott invariant, which is a simpler collection of information than the C-star algebra itself. And I'll mention in a second what some of the components of this are. And if the data contained in this invariant agrees for two C-star algebras, this happens if and only if they're isomorphic. So this thing, the Elliott invariant, can distinguish two C-star algebras from one another. But the actual, perhaps more powerful direction is that if two C-star algebras have the same Elliott invariant, then they are in fact isomorphic as C-star algebras. And so this is named after George Eliot, who was one of the founders of this line of research. And so we often refer to this as the Elliott classification problem. It says the following. If you take a simple, unital, separable, nuclear C-star algebra, so the conditions here, simple means no non-trivial ideals, unital means it has an identity, separable means it has a countable dense subset, and nuclear I'm not going to define, but I'll mention in a second what that's about. So we want to say, can it be classified using its Elliott invariant? And this is roughly what's considered, it's K-theory and its traces. So K-theory itself is a complicated branch of topology, but the basic idea here is that K-theory is essentially group theory when it comes down to it, because what you get are groups. And so you're trying to replace the C-star algebra with just a group and then some other information. We're called its traces. And then something else called the Kuhn semigroup. And I'm not going to talk about this, but it's a newer object that's been sort of brought into this by necessity. Essentially, Andrew Toms found that there are C-star algebras which sort of fit what we want to be the classification program that cannot be distinguished through their Elliott invariants. But this other thing, the Kuhn semigroup, can do it. So it's an obnoxious piece of data that has sort of had to be brought into this idea. Okay. The condition nuclear is required here, and if you drop it, then the answer is definitely no. Being nuclear is a very technical condition, but essentially what it is the right condition to think of classification. So the nuclear class is the largest class where classification theory is at all reasonable. Once you're outside of this, too many bad things can happen. All right, so these are the types of things we like to study. Is we take these C-star algebras satisfying these conditions and try to figure out if we can find classes of them that satisfy certain what we call classification theorems. So just for an example that I didn't put in the slide, suppose your C-star algebra is the direct limit of matrix algebras. So in other words, it has a direct system of finite dimensional dense subalgebras. Well, then we call this an approximately finite dimensional algebra, or AF algebra. And it's known that all such things are classifiable. You can prove a classification theorem for these. And there's other classes of things like this as well. So a lot of what we do is trying to see that, well, new algebras we come up with can fit into one of these classification theorems that tell us that they, in fact, are classifiable. All right, so today I want to talk really about a fairly special type that's received a lot of study over the last 20 years or so. But to do that, I need to introduce some topology, specifically topological dynamics. So take a compact metric space and a homeomorphism of H of the metric space X. And then the pair X, H is referred to as a dynamical system. The dynamics are essentially given by applying H to the space over and over again. Now it's a homeomorphism, so it sends X back to itself, but it moves the individual points around. So here's a few examples of this. This is perhaps in some sense the most classic one, at least from the point of view of C-star algebras. Take the circle, which you can identify with the unit circle in the complex plane, fix a real number, and take essentially rotation, a real number theta, and let your homeomorphism be rotation by 2 pi theta. As we'll see, that the dynamics here change quite a bit depending on whether you choose theta to be a rational number or an irrational number. For another example, take X to be the sphere across the sphere, which we can identify as the torus, and then pick some extra information, and then define a homeomorphism of S1 cross S1, so the torus given by this formula. So there's quite a bit going on. In the first slot, you have a rotation, and in the second slot, you have a rotation that actually depends on a function of the first slot, and then also a sort of dilation of the first coordinate. This is called a Furstenberg transformation on the torus. And it's known that these homeomorphisms have nice properties that makes them accessible. These were introduced by Furstenberg back in, I think, the 1960s. So they're one of the older classes that are around. And then for maybe the most classical example of all, although I'm not going to give any specific examples. If X is the Cantor set, then there are lots of interesting homeomorphisms that we can look at, and lots of dynamical systems we can get. Now in this case, the ones for the Cantor set are actually a little more complicated to write down, but for the most part. There's no sort of really easy ones to just state, but there are lots of different explicit examples that can be formulated. Usually by viewing the Cantor set as either the p-adic integer, the p-adic numbers, or viewing it as the set 0, 1 cross itself infinitely many times, and so on. There's lots of other formulations of the Cantor set that give us these. Okay, so now I want to talk about a C-star algebra construction called a cross product. I'm going to specialize here to the commutative case. So when our C-star algebra is the continuous functions on a space. So we take a dynamical system, and usually it'll be infinite. So the set X is an infinite set, so not a finite collection of points, but it has finite dimension. So if we have a homeomorphism H, then this actually induces an automorphism on the function algebra C of X, given by composition with H inverse. The inverse here is to make sure that it actually is an automorphism rather than, say, an anti-automorphism. And so what this gives is an action of the integers on the automorphism group of C of X, given by, well, an integer maps to a power of alpha. We define a formal unitary here meaning an element who multiplied by its conjugate gives the identity. And the unitary is essentially supposed to implement the action of this automorphism alpha by conjugation. So in other words, if we take a function and we conjugate it by u after u star, then this gives us alpha of f. It applies the automorphism alpha to the function f. And now we define this thing called a cross product. We denoted C star ZXH, the cross product C star algebra of X by H. It's the universal C star algebra generated by all the functions in C of X in this formal unitary U. And this is sort of a quick and dirty definition of it. It's actually quite a bit more involved to define this thing. Because you have to actually, you essentially define a group algebra, and then you need to define a norm on it, but the norm's not complete, so then you need to make a universal representation and complete the universal norm. And it's all very technical, but this is essentially the right way to think about it. The elements of it look like continuous function, things you can get using continuous functions on X and this unitary U. So this is the relation UF U star equals F composed of H inverse is this conjugation relation. This tells us essentially that what we have now is a non-commutative algebra, even though we started with a commutative one, because this says that UF is equal to F composed of H inverse U, if you move the one U over to the other side. So what we do basically is we take a commutative C-star algebra, continuous functions on X, and we build a big non-commutative C-star algebra out of this. And so then the question is, well, what properties does this non-commutative C-star algebra, this cross product, have? Oh yeah, one last little thing. Sometimes in this case, this is also referred to as a transformation group C-star algebra. It's just sort of some special terminology for the commutative case. This construction can be massively generalized, not only to different C-star algebras, but also to different types of group actions. So you can simply, you don't need to look at the integers, you can look at lots of different types of groups. Finite groups, countable groups, there's all sorts of possibilities here. So it's a very general construction to build new algebras from old ones.
So should this U, should I be imagining it as a function on X or as some abstract object?
You should be imagining it as an abstract object, essentially. It's a formal unitary that we're introducing. But specifically, sort of good elements of this thing, the ones that you actually want to work with, essentially look like formal power series in U. So you're going to have functions fn and then powers of U, and all but finitely many, for instance, of the fn's are 0. You essentially start with the ring of power series like this, and that's your kind of your basic starting point for the construction. So you have elements like this, but you actually have a lot more because you've done a huge universal construction over top of these. Okay. So I want to point out how the dynamics given by the homeomorphism H come into this, into these cross products. So the basic idea here is that the properties of this thing don't just depend on the space X, so in other words on the continuous functions over X, but they depend quite a bit on the homeomorphism H in the dynamical system. So here's an example using one of the ones we looked at earlier. So let's take this rotation map on the circle, given by rotation by 2 pi theta. And then this transformation group C star algebra, C star Z S1H, is often denoted by A sub theta. Well, if theta is 0, then A sub 0, A theta in this case, is the continuous functions on the torus. So it's a commutative C star algebra. It's not simple, and it contains no non-trivial elements that we call projections. The homomorphism in this case is just the identity map, because we're rotating by the angle by nothing. We're not using a rotation at all. So you get a commutative C star algebra in this case because when you apply the powers of the homeomorphism, nothing happens. All right, well, if you take theta to be P over Q, a rational number, then we call this a rational rotation algebra. Take it to be a non-zero rational number. Now it's not simple. It's still non-simple, but it's also non-commutative, because now the relation U star equals alpha of F actually does something interesting. Now if you take a point x in S1, then its orbit under this homeomorphism is finite. There's finitely many powers of h you need to apply to move the point back to where it started, and so it's actually a closed set. All right, and finally, we'll see the most interesting case. If theta is chosen to be an irrational number, then we get A theta and call it the irrational rotation algebra. Now this is a simple C star algebra, so it has no non-trivial ideals. It's non-commutative, and it has a property called real rank 0, which means it contains many projections. Projections are, in some sense, very nice elements in a C star algebra. They're self-adjoint idempotents. And the more of them you have, the easier it is to essentially study the algebra. And in this case, if you take a point x and you look at its orbit under the homeomorphism h, then this is dense. So as you move around by an irrational number, you get a dense subset of S1. All right. So now I want to actually identify what's happening in the third example through a definition. So it's from the point of view of classification theory, it's the most interesting, because we want simple C star algebras typically when we're doing classification. So here's the property that distinguishes that homomorphism from the other ones. We call a homeomorphism H minimal if there are no non-trivial H invariant closed subsets of the set X, or equivalently, if the H orbit of every point is dense. And so that was what we saw in the third example, the irrational rotation, but it certainly wasn't true in either of the first two. So if H is minimal, then this cross product is always simple, assuming X is an infinite set. So this is there's of course some work that goes into this, but this is one of the first really accessible results we get. So this is at least the right type of thing to be studying. And then if you introduce additional hypotheses into your situation, then this cross product C star algebra can have a lot of good structure properties. So here's a theorem. This is sort of like the culmination of everything. This is about a decade of work going into this. And I put a couple of names on here: Hua-Xin Lin, Xing Lin, and Chris Phillips. And there are lots of other people that sort of contributed to this, but these were really the three big ones. If you assume sufficient things about the K-theory of this cross-product C-star algebra, you make certain assumptions, essentially that it has enough projections and enough finite-dimensional subalgebras, then it has a property called tracial rank 0. Now earlier, remember, I described that if you have a direct limit of finite-dimensional algebras, then we consider this approximately finite-dimensional. That is an approximate finite dimensionality in a very strong sense. Tracial rank 0 is a sort of very weak approximate finite dimensionality, much weaker than this AF condition. So it's much easier to verify that something has this property. Nevertheless, it turns out that tracial rank 0 C-star algebras can be classified. This was one of the biggest results of the early 2000s, is that these algebras with this weak approximate finite dimensionality are actually classifiable, always. This theorem sort of, in some sense, didn't quite close the book on the study of these algebras, but it showed that under the right conditions, they have very good properties. They're exactly the kind of things we want to look at. In fact, it spurred even more study of them because it showed people that they form an interesting class of objects in the classification theory. Okay, so what I want to talk about is a little bit into, not of course, into what goes into proving this theorem, because The backbone of this theorem is a 200-page unpublished preprint that's not even on the archive yet. It's just on my supervisor's computer that needs editing and he doesn't want to do it. And then a couple of 40-page papers on top of that. And so it's a lot of work, and then some other results as well. So we'll see if it ever actually gets published. I don't know. But I want to give some idea of the techniques to go into studying this. The overall point here is that a lot of the properties of this algebra can be obtained just by essentially looking right down at the base, at the space X and the dynamics on X. You don't need, at least at first, a ton of the actual sort of C-star algebra machinery. A lot of it is, in some sense, topological dynamics. Okay. Well, it turns out that this algebra, as I've kind of mentioned a few times, is in some sense very large and somewhat intractable to just attack directly, to look at. You might think, okay, well, if you could look at elements like this, then that works out pretty well, but in fact, it really makes it quite difficult to do. So what we do is we actually introduce a subalgebra of this. This subalgebra, it turns out, is much easier to work with, much easier to sort of attack directly, but its properties can actually pass to the whole thing. So what we do is we fix a closed subset Y of X, usually small in an appropriate sense, and define a subalgebra Y, A sub Y as follows. You look at the C-star algebra generated by all the continuous functions on X, and then all the things in the form U times a C0 function on X complement Y. And the right way to think about the last thing is C0 of X complement Y is the subalgebra of all functions on C of X that vanish on the closed set Y. The sort of perhaps somewhat informally, the way this algebra is sometimes described is you have this unitary U, and what you want to do is you want to sort of break it into pieces every time the orbit of a point passes through the set Y. And that doesn't quite make a lot of sense until you actually sort of go through doing everything and see kind of what that describes. So this algebra is a subalgebra of the cross product, and we'll take a look at some of its properties in a second. So this was introduced by Putnam in the case where X is the Cantor set. And it turns out in that case that these subalgebras actually have this AF property of being approximately finite dimensional. And then Xing Lin generalized this to more general compact metric spaces that are not the Cantor set, in particular ones that are connected. And this is sort of where all hell breaks loose and everything gets exponentially more complicated in a hurry. The Cantor set is just so much easier to work with from a C-star algebra point of view than any other topological space. Okay. So what we do is we don't just want to look at a closed set Y, we actually want to look at a very special closed set, a singleton point. So choose a sequence of closed sets that are nested, decreasing, and whose intersection is a single point. Then if we look at the subalgebra formed by this single point, it's actually a direct limit of these subalgebras using these Y sub n's. And we can think of this as simply the closure of the increasing union of all these subalgebras. So we can take a subalgebra which uses a closed set that is in a sense as small as possible, a single point, and then write it as a closure of a union of some other slightly larger, well, smaller subalgebras using larger closed sets. All right, here's some results that I'm going to state a little informally. Well, this subalgebra A sub single point is a simple algebra, which is good. It's a large subalgebra of the whole cross product A in an appropriately defined sense. And in particular, properties of this subalgebra A sub little y can pass to the whole cross product A. Certain ones, not all of them. And then when you take a closed set capital Y with non-empty interior, then it turns out that A sub y is something that we call a recursive subhomogeneous algebra, which is a very technical definition, but essentially it's an iterated pullback construction of algebras of the form continuous functions into matrix algebras. And then A sub y is a direct limit of such things. So remember I said earlier that direct limits of algebras like this can turn out to be lots of other things, and this is an example of this. So a recursive subhomogeneous algebra is essentially a weird subalgebra of the direct sum of a bunch of such things. And then in particular, a lot of the properties of these subalgebras, where the y has non-empty interior, are preserved by direct limits. So they pass to this subalgebra A sub little y, and then they go up from there to the big subalgebra. So there's a lot kind of going on here in the sense that we're sort of digging down into our cross product until we find algebras that we can work with, but then lifting the properties back up through various constructions. Okay, so the recursive structure of these things is what makes them easier to study, and hence this approximating subalgebra. And again, this is done sort of topologically through what are called Rockland towers. So the Rockland tower construction is something that was originally introduced in ergodic theory with basically measurable dynamics, and then was sort of introduced into the topological case. So we have the following thing. I don't want to spend too much time going through this. You take a closed set Y with non-empty interior. Well, for each point in Y, there's a finite amount of time that it takes for that point to land back in Y by applying powers of the homeomorphism. We call this thing the first return time. So there's finitely many of these, finitely many distinct values because they're integers. Well, then what we do is we define sets. We break Y up into pieces. We define a set Y sub k to be all the points in Y whose first return time is an integer n of k. So there's, we break up Y essentially corresponding to the first return times to Y. But then we have to take the closures of these sets. And then we take the interiors of them as well. Well, what does this do? What we get is an interesting sort of almost partition of the space. I'll put these up and I'll describe what they say. Well, okay, try not to step on the cord again. The middle one, the middle property says that these Y sub k's form all of Y. So all the points in Y can be partitioned using these first return times. Oh boy. Maybe I should just stand up here. Okay, can I go backwards? Yes. All right. The first property says that the interiors of these things are pairwise disjoint under powers of the homeomorphism H. And then the third property says that if you iterate H over all of these sets, the closured ones, the Y sub k's, you get the entire space X. So let me try to draw a little picture to describe what's going on here. We've got our base Y that we break up into pieces. So here's Y down here. And then over each of these pieces we have these levels, which are formed by taking, iterating the homeomorphism. So this would be, say, H of Y0 right there, H squared of Y0, and so on. This would be H to the n of L minus 1 of YL, etc. So you've got all these you've got these columns and then levels in the columns. And the idea is that the union of this entire picture is all of X. And the union of the base row is, the base level essentially is Y. And that each level is almost disjoint from all the others. They're disjoint on the interiors, but not necessarily on the boundaries. So when you push Y0 up to H of Y0, these two sets are disjoint except possibly on the boundaries of the sets. When you get to the top of the tower, it doesn't necessarily push you back down into the level below, it pushes you back into the base somewhere. And then you start moving up again. And you can kind of move through the space in this way. Okay. In the case where you have the counter set, you don't need to take closures or interiors, everything's disjoint and it all works out incredibly well. And if it's not a counter set, then it doesn't. So we need to introduce a little bit of measure theory here, and here's why. So this Rockland tower construction allows us to break X up into a bunch of pieces which are close to being translated.